Hello. So this is the demo for the advanced pytorch for deep learning. So yeah, so this is just the initialization and GPU setup. So yeah, so in part one we'll use AutoGrad for simple gradients. Earlier we used AutoGrad. Now we'll explore nested AutoGrad for higher order derivatives, Jacobian and Hessian computation, and compute gradients with pytorch, pytorch.autograd.function, and gradient hooks for manipulation. So yeah, so this is the code for it. It uses autograd.grad, and it also grade graph is true. This is for to continue differentiating. uh, so yeah, so let's say the function is x raised to power 4 and evaluate at x equals to 2. So f of x will be 16. 2 to the power 4 is 16. But f dash of x will become uh, 32, and second order of it will be 48, and third order again will be 48, because yeah, why this happened is because it was x raised to 4, but when we differentiate it again, so it will be 4 x raised to power 3, and 4 into x raised to power 3 is 8, which is 32. Then second differentiation is, again we are differentiating 3 into x to the power 4 into x to the power 3, so it will be 4 into 3 into x to the power 2. So 4 and 3 is 12, and x to the power 2 is 4, so it will then be 48, and then again 12 into x to the power 2 will be differentiated again, and it will be 12 into 2 into 1 into x. So that's why 24 into 2 has happened, and we got so as you can see the differentiation happening over here. Now let's look at the Jacobian computation. So Jacobian is the matrix of all first order partial derivatives, and for f, r raised to n will become r raised to m, and the Jacobian is m cross n, where j of ij will become the differentiation of I by j. So let me just give an example. Yes. So this is my x vector, and this is this is the equation. So x1 raised to power 2, x1 into x2, and sine of x3. So here you can see x to the power 1, x1 raised to power 2 is 1, so we got 1. X1 into x2 is 2, we got 2, and sine of x3 is this value. Now the Jacobian matrix will look like this: 2 0 0, 2 1 0, and 0 0, and this minus negative. This is because of the this is the as I mentioned that Jacobian is the first order partial derivative matrix of first order partial derivatives. So here you can see this is basically differentiation of x1, which is 2x1, 2 into x1, so that's why we got 2 here, and here it is differentiation of x2, so basically this whole column will be differentiation based by x1, this will be by x2, and this will be by x3. So x this with x1 is 2x, this by x1 will be x2, and this will be 0 because x1 is not available here, so this will be treated as constant and the constant's derivative is 0. Then we have this, now this row this column will be derivative of x2 based on by x2. So x1 raised to x1 square, as there is no x2 variable here, this will be again treated as constant and the value will be 0. Here the value will be x1, and again x3 will be, this one will be 0. And same for now, we will do the partial derivative for x3. So this is will be 0, this will be 0, and this will become sine's derivative is cos of x. Sin x equals derivative is cos x. So we'll just yeah, this is the value for that. And yes, so this is how the Jacobian matrix looks. Now let's look at the Hessian matrix. So Hessian matrix is the second order. So Jacobian is first order partial derivatives. Excuse me. Just Hessian is second order partial derivatives. So again, here we are using a different equation, x square into y cube. Now these are the only two variables we have used. Now the matrix will how the matrix will look like is first we will, again the first will be the first column will be based partial derivative of x, and the second will be partial derivative by y. Now let's do this, find out the partial derivative with respect to x. So here y will remain as is, and we will differentiate it, and it will get 2x. So sorry, x to the power only 2y. So that's why we got 2y, and 2y is 2, that's why the value is 4. Now for x, okay, this is the whole equation, my bad. So this will become only y through, and this will be treated as constant, so 0, so plus 0. Then now let's do this based on y. Y will be 2x and plus 3y square, excuse me, and as I mentioned that it will be a second derivative, so we have to again differentiate it. So so this is the first first derivative, first order, and so yeah, let me just rephrase it. So first derivative will be xy with respect to x is 2xy, and this will be treated as constant, so nothing put there. And now derivative with respect to y will be x square, and y will be 1 plus plus 3 to the power 3 y raised to 2. So this is the first order. Now we will have to compute it second time, because that is what the Hessian is. It is second order differentiation. So now when we'll again differentiate these values, we will get again this based on x will be 2y, and here it will be 2x, and this will be constant, so that's a 2x. Now with respect to y, it will be 2x So we got 2x, and this will be constant, and this will, 2 will come forward, and 2 into 3, 6, and y. So that's why 6y has come, and this is how the Hessian matrix is computed. Now let's look at the custom autograd functions. So we have this we are creating this clip gradient norm, which is inherited from the torch autograd function. And yeah, so again we are having a forward function here and a backward function. So forward is and then we are calculating it. Now this is a straight through estimator used for binary discrete operations that are non-differentiable, and used in quantization in neural network. So in the forward pass it will round to nearest integer, and the backward it will pass the gradient through unchanged. So that is there. Then we have hooks. So hooks allows you to inspect or modify gradients using backward pass. And register hooks function on tensors, and register underscore background hook on modules. So yeah, that is what is happening over here. And yeah, hooks are powerful for debugging gradient flow and gradient clipping per tensor, and feature visualization, like when you want to see how the gradient is moving. For that it's quite useful. Then we have gradient accumulation. It is useful when the batch size is too large for GPU memory and you want efficient batch sizes. So again, it is the pattern is you have to use optimizer at 0 grad once at start, so that when a new epoch runs, the gradients are set to 0. Then we have to scale the loss by 1 divided by accumulation steps. Then we have to call loss dot backward function, which will accumulate the gradients, and optimizer dot step is where the gradients will be back propagated and the values of weights and biases will be changed. Then we have effective batch, which is mini batch into n. Then building operations from scratch. So understanding neural network primitives before using NN dot module layers. Let's understand what they do by building them ourselves. So yeah, this is a convolutional network layer. Yeah, so we are creating a convolutional layer, and we have created an input shape, a kernel shape, and an output shape. And now let's do max pooling from scratch. So this is a very naive max pooling implementation, and for each pool size and pool size window, take the maximum value. So that implementation is happening over here. Then we have batch normalization from scratch. So batch normalization implemented from scratch. So during training, x underscore norm equals to x minus batch mean and divided by square root of batch var plus epsilon, and y equals to gamma plus x norm, gamma multiplied by x norm plus beta. During inference, using running mean and variances instead of batch statistics. So this is we have initialized over here the batch norm, and now we are calling it. Then we are doing the same for layer normalization. So we are normalize across features, not batch. So it is used in transformers because it works with any batch size, Yeah, it makes sense, right? For any batch size it will run, whereas the batch is, it's for that particular batch, and no running statistics needed. Each sample normalized independently. So yeah, that is defined over here, and we are calling it. This is the formula for that, and this is how the scale and shift working. Yeah. Now we have dropout. So dropout is randomly zero out neurons during training. So the key insight is scale by 1 divided by 1 minus rate during training, so that expected value remains the same during inference. So yeah, that is the idea behind a dropout, and we are just implementing that. We are creating a random mask, and that applying that mask and scaling it and returning it. Then we have custom layers using primitives, building layers with nn dot parameter only. So before using pytorch layer classes, let's build fully functional layer using only basic operations. This shows exactly what happens under the hood. Yes, so we are creating this dense layer primitive. We are giving in input output features, user bias, the activation function. We are creating the tensors. Mm. Now the dense layer is created. We are creating a 2D layer from primitive. So here we have the stride padding and the use bias, the kernel size, activation function, everything is defined. Then we are creating a tensor for kernel, for the bias, and then we are in the call. We are calling the convolutional 2D using kernel, bias, stride, and padding, and we are just returning the activation of it after applying activation to it, and we are returning it. So that is how we got our convolutional layer. Mostly this is very this is from very basic implementation. We have this inbuilt in pytorch, where you can just use it from the existing library, but this gives how the things are working under the hood. So yeah, and now this is the complete convolutional neural network. So complete network built using only primitive layers, which we have created right now. We have a 3x3 convolutional layer. It will then pass to a ReLU, then a max pool, and again a convolutional of 3x3, then ReLU, max pool, then we'll flatten and dense. This is the overall view of our convolutional network. Now we'll just put this sequence in our main model. So we have the we need two convolutional network, which is 3x3 matrix with ReLU and max pool. So we are just passing those value over here. Then these are calculate flatten size after convolutional and pooling with the same padding, and 2x2 pooling twice, which is S by 4 and W by 4. Then we are creating dense primitive layers, because we need two dense primitive layer. And yeah, now we have this we are creating this max pool, because we have to apply max pool twice. So we are creating one for convolutional 1, one for convolutional 2, and then we are flattening it, and yeah, then we are applying dropout. And yeah, so this is how the convolutional primitive, using primitive functionalities, we have created a convolutional network from scratch. Now let's use the NN model. So here we'll just inherit from NN model, and yeah, so we'll just call the super initialize our variables, and the weights, we are initializing the weights, the parameters, register parameters, activation function, and in the forward pass we're just passing the matrix multiplication and adding the bias if it is there and returning with activation. So this is our basic layer using the module. Now let's create a self attention. So we are again we have this self attention layer, which is again inheriting from the NL module. Here we can just attention layer is simplified version of transformer attention. So attention is it takes Q, K, V, and it is basically softmax of Q matrix multiplied with K transpose divided by square root of dk, and then again matrix multiplied with V, which is the value vector. So in self attention, K, Q, V all come from same input. So yeah, that is what is implemented here. We are creating the KQ vector. These are the weights for Q, these are the weights for K, the weights for V, and output. Then we are initializing the batch, reshape for multi-head attention. Then we are that formula, this formula is being implemented over here. Then we have we are masking if it is required. We are then doing softmax. Then again the formula which we have shown, it is getting implemented, and that is how attention layer is created. Then we have the spectral normalization. So spectral normalization wrapper for linear layers. So it constrains the spectral norm, the largest singular value of the weight matrix, used in GANs to stabilize training. So it basically normalizes your the weight of your layer, so that it doesn't go beyond certain values, so that then we can have the exploding gradient issue. So yeah, that is what is created over here. Then we have this residual block. So now let's build an architectural component using state-of-the-art models. So residual block is also known as ResNet. Then we have squeeze and excitation, which is SENet. Then we have transformer encoder block. Then we have custom normalization layers. So this is the residual. Let's start with the residual block. So here it is f of x plus x is my output. The key insight is learning residual f of x equals to y minus s is easier than learning x directly. This enables training very deep neural networks. So again we are creating one convolutional network, one batch norm, again a convolutional network, again a batch norm, and again we are passing it to an activation function and adding the bias and returning. So that is our residual block. Then we have squeeze and excitation. Squeeze and excitation is squeeze is global average pooling. So we're just pooling the H and W to 1 and 1, and then excitation is ReLU to FC, then sigmoid. So we are multiplying input by tension weights, and so again the excitation layer is like this. We are calling a sequential layer of linear layer, then ReLU, then again a linear layer and a sigmoid, and so now from now on most of the things will be same. It's just these formulas, the how the layers are placed one after another is how it differentiates its functionality. As you can see, it's everywhere it's same. Again here I'm calling an sequential model and just passing it in this format, and this is an encoder transformer block. This then again will be the yeah, the one which we the excitation squeeze excitation block. It's just that, and how what that differentiates when I change the sequence, and when I add a new layer or a new block, what how its functionality changes is what differentiates that. So then the training loop is as is. We are just with every epoch we are first training the model, setting the gradients to zero, finding the outputs, then loss, then calculating the optimizer gradient, which is calculated using loss dot backward. Then optimizer dot step is where the gradients are activated and the values are changed based on the gradients. So yeah, that is pretty much it in this notebook. Thank you.